Hello, and welcome to this episode of Madison's Chemistry. The goal of this video is to be able to walk you through a weak acid strong base titration so that at any point in the curve you know how to find the pH. Okay, so let's start at the beginning. Say a question gives you something like you have, 0.1 molarity of acetic acid, so HC2H3O2, and you have 100 milliliters, and you titrate with NaOH 0.2 molarity. So what's the initial pH before any NaOH is added? So this question is basically saying at this point in time, what is it before when we have 0 milliliters of NaOH? What is the pH? So to solve this question, it's really not too bad. It's something you guys are pretty familiar with. So if we want to find the pH here, so the Ka equals H3O plus times A minus divided by HA, and we just solve for this and take the negative log to find the pH of the initial value. And the Ka will be given to you. So for example, for acetic acid, it's a known Ka, it's 1.8 e to the negative fifth, so you could just plug that in and solve for the H3O plus concentration. Okay, so now let's go ahead and look at any point in this region here. This is a really guesstimate. So let's say this here is our buffer region. Okay. So if we're at our buffer region and we're asked to solve, we can actually use this equation called Henderson-Hasselbalch, which I'm sure you guys are pretty familiar with now. Hasselbalch, or HH, which is the equation that states our pH equals the pKa plus the log of our A minus concentration over HA. So we can pretty much use the HH anywhere in there. The point that's actually especially unique is the half equivalence point. So let's say that this right here, half equivalence point. So the half equivalence point is where our moles of A minus equals moles of HA. And at this point, our pH equals our pKa. And this makes sense if we're looking at this equation, because basically it's saying that at this point, it's equal to log of, x over x, which is just 1. So this is just log of 1, which is 0. So that's where we get this pH equals pKa at the half EQ. Okay, but yeah, we can use this equation anywhere within the buffer region. So what about at the equivalence point? We know that weak acid, strong base, it's not as simple as it's going to be a pH of 7 at the half equivalence point, or at the equivalence point, so how do we find our pH there? So this is going to involve a little bit more steps. So let's say we have HA plus NaOH A minus. So let's say we have 0.01 moles of each, right? Because we know at the equivalence point, that's where the moles of weak acid equals the moles of strong base. So we have 0 moles of each of these in solution right now. But we do have 0.01 moles of A minus. So what we would do to find the pH here is we would say, okay, A minus H2O goes to go form HA plus OH minus. So this is now minus x plus plus X. So this is just a normal ice table. And then you would use the KB. And remember, the KB you can derive from the KA. So the KW equals KA times KB. So therefore KB equals KW over KA. So you can definitely solve for the KB. And we know we're given the KA from earlier. Okay, so that is how we could find it here. So basically you'll find moles of A minus and calculate pH with the KB. Okay, so let's go back to this problem to figure out how we'd solve it. So we're really solving for the moles of OH minus here because KB is going to be equal to OH minus times HA over A minus. So then we could definitely go ahead and find the pH from here because we'll find the pOH and we can find the pH. And then last but not least, this is probably the easiest, is when we have excess OH. So if we have excess OH, how we find it, so let's say we have HA is 0.01 mole, and we have NaOH is 0.02 moles. So we're going to run out of acid, but we'll still have 0.01 moles here. So all we have to do here, we're going to assume that all of this is going to go form OH minus. So we'll just do molarity equals moles divided by total liters here. So remember, you have to add acid plus base liters. And then you can do the negative log of OH to find pOH and then find pH. So this is probably the most simple one. So if we're in this part of a graph, we can just do like normal negative log of OH concentration equals pOH. So each of these points, this is kind of what I was trying to get at with this video, is we can look at any point in our graph and determine the pH. So we know that if it's the initial, we can just do this, the Ka. If it's in the buffer, we're going to use Henderson-Hasselbalch. If it's at our equivalence point, we're going to have to find what our moles are and then go ahead and find A minus. And then last but not least, excess OH, we can just assume that there's so much OH that, because technically, if you wanted to go back here, we would be forming some A minus. So the reason that we don't have to consider this, the 0.01 mole that's forming of A minus, is because it's negligible compared to this. So we're only going to be focusing on the NaOH. We can ignore the amount of A minus that's produced there because it will not have as significant of an effect on pH. So yeah, so this is how we could find all these values. It's going to be very similar for a weak base, strong acid titration, so that could be useful to go ahead and go through on your own, like creating this chart where you can determine what you would find, like how you would find it at each specific location. So I encourage you to do that on your own. I hope this video was helpful. If it was, I will be posting more videos every week for Gen Chem 2 if you want to subscribe, and if you have any ideas for future videos, I'd love if you made a comment below. So thank you for your time.